All right, so now we're going to talk about tangents and secants, okay? So I'm going to put some stuff underneath to make this a little bit easier to see. All right, so our first definition is a tangent. So a tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. All right, so another way to think of the word tangent is tangent also kind of means next to or adjacent. Okay, so you can kind of think about it like that, where a tangent line is a line that's like next to the circle, if you will. Okay. Now I don't. All right, so really quickly before we get into the rest, I want to talk about another word, point of tangency. I don't know if, oh, yes, we are going to, oh, no, I don't know. No, I lied. I thought it was coming up, but I guess it's not. But really quickly, the point of tangency is that intersection point where the tangent line hits the circle. Okay, so at this point, point P is the point of tangency. So where the tangent line touches the circle. Okay. All right, so now we have another definition. So a secant of a circle is a line that intersects the circle in 2 points. So since this line, be careful, it's a line, not a segment, a line intersects the circle right at this point and this point, this is a secant. Okay. So now we have another theorem, another idea, if you will. So if a line is perpendicular to a radius, perpendicular to a radius at its point of intersection with a circle, the line is tangent to the circle, okay? So let's think about it like this. So say if AB is the tangent line and OP is the radius. So we're going to call OP the radius and AB is the tangent line. And they intersect at the same point, so the point of tangency, if you will, it's going to be perpendicular. Okay, so it's going to create a right angle there. And this is exactly what I just said. So if the line is tangent to the circle, the line is perpendicular to the radius drawn at the point of tangency. Okay, so like I said, AB is our tangent line, OP is our radius. Now, if they intersect at that point of tangency at the same point, then it creates a right angle. Then they're perpendicular. Okay. All right, so let's go on to the next page. Okay, so now we have another definition. There's a lot of definitions. So a common tangent is a line that is tangent, so it touches the circle to each of 2 circles. Okay, so let's take a look at some examples and then hopefully this will make sense. So let's take a look at case 1. Now I have circle 1 and I have circle 2. Now this dotted line is the imaginary line where it's connecting both of their center points. Okay. So this is my tangent line. Now AB is a internal common tangent because it is like kind of inside the circles, if you will, okay? And it's touching the circles touching both of the circles. Okay. Now, this is another case of an internal tangent, whereas because the tangent line is crossing that imaginary line connecting the two centers, but the circles are touching, so they have the same point of tangency. Okay. All right, so now we're going to talk about external tangents, external common tangents. Now, one thing to know about common external tangents is that they do not intersect the line segment joining the centers of the circles. Okay, so for example, this one, as you can see, the two centers are connected by this line. Now, this tangent line touches this circle and it touches this circle. Okay, but as you can see, unlike the internal tangents, the external tangent does not cross the imaginary line connecting the two centers. Okay, and there can actually be another tangent line here. Okay, so it can be one here, but there can also be one here. So I'm going to draw in another tangent line here. Okay. Now, our case 2, if we look at here, so these are what we call concentric circles. Because one circle is inside the other. Okay. So two circles can have more than one line that is tangent to both circles. So obviously up here, as you can see in case 1, we have one line, we have another line, but we can also draw in another internal tangent line, right? So, I mean, I'm not going to, I'll do it. So, because remember, internal, they crosses the center line. So we can draw an internal tangent line here. Okay. So they can have more than one line. More than one common tangent line. All right. So let's go on to the next page. All right, so another definition. Yay, we love definitions. All right, so this definition is a tangent segment. Okay, so a tangent segment is a segment of a tangent line. So it's part of the tangent line, whose one of whose endpoints is the point of tangency. Okay, so we have let's look at this diagram here. Now the points of tangency is Q and R, right? Because that's where the tangent line connects, like touches the circle. Now, so the tangent segments, like I said, are part of that line. So this is a tangent segment and this is a tangent segment. Okay, so tangent segments in this diagram are PQ and PR. Okay. Tangent lines, on the other hand, are as line PQ and line PR. Okay, so remember the difference between a segment and a line. Okay, a segment has two endpoints, whereas line, they don't. All right. So, and now another theorem. So, tangent segments drawn to a circle from the same external point are congruent. Okay. So now, since PQ, segment PQ, and segment PR are drawn from the same point P, PQ is going to be congruent to PR. But they have to be drawn from the same external point and touch the circle at only one point. So this only works in this case right here. Okay, so since they only touch the circle once, and they're drawn from the same exact external point, PQ, this segment and this segment PR are congruent. Okay. So on to the next. So if two tangents are drawn to a circle from an external point, the line determined by that point in the center of the circle bisects the angle formed by the tangents. Okay. All right, so let's see what this means. Okay, so as we just learned, if the tangent segments drawn from the same point intersect the circle once, they are congruent. Okay, so we know that PQ and PR are congruent. Okay? We also know that if the tangent line and the radius intersect at the same point, then it forms a right angle. They are perpendicular. Okay. Now, if there's a line, this dotted line here is drawn to the center from the external point, it's going to bisect this angle. So this imaginary line here is going to bisect this angle P. So this angle is going to be congruent to this angle here. Okay. Now, as you can see, since these two triangles, since this triangle has a right angle and this triangle has a right angle, we have two right triangles here. So this is triangle number 1. This is triangle number 2. Okay, so we have two right triangles. Now we have to be super, super careful though, because this line, the line that was drawn, is actually the hypotenuse. Okay. It looks kind of weird, but remember the hypotenuse is across from the right angle. So this line drawn is going to be the hypotenuse. Now you're going to get questions. Where are you given this length and this length, and you have to find this length, and you're going to have to use Pythagorean theorem. You have to be very, very careful that this line is your hypotenuse, and you have to remember that. Okay? Okay, cool. Let's go to the next one. So, now when a polygon is circumscribed about a circle. Okay, so let's talk about what the word circumscribed means first. Now, the word circumscribed essentially just means drawn around another. So a polygon is literally drawn around the circle. Okay. So a polygon, like I said, is drawn around the circle and it's touching the circle. Okay, at a couple different points. So a polygon is circumscribed about a circle if each side of the polygon is tangent to the circle. So like I said, when you circumscribe something, you draw it around, but it still has to touch. Okay. So the circle O is circumscribed in polygon ABCD. You want to state the 4 points of tangency. So we want to state the 4 points where the polygon touches the circle. Okay. Now this is a point. I mean, it doesn't look like this, the diagram, but this is a point of tangency. This is a point of tangency. This is a point of tangency. This is a point of tangency, okay? So the 4 points of tangency are F, G, H, and E. All right. So let's do some examples. All right. So our first one. ABC is circumscribed about a circle. So ABC is drawn around circle. And D, E, F are points of tangency. Okay. So first of all, let's think about this. So these are all points of tangency. So these are all segments, tangent segments, okay? And what we just learned about tangent segments is that tangent segments drawn from the same point are congruent. So AF is congruent to AD. BD is congruent to BE. CF is congruent to CE. Okay? Now, we have some links here. If AD is 5, EB is 5, and CF is 10, we want to find the rest of the lengths. Okay? So now, like I just said, AF is congruent to AD. So if AF is 5, then AD is 5. So AD is equal to 5. Oh, they're not even asking for this, but we'll just write it down right now. Okay. Now, if this is 5, this is also 5. So BD is 5. Okay. CF is 10. So CE is 10. Okay, now let's find what they're actually asking us to find. So we want to find the lengths of AB, BC, and CA. So AB is this. AB is this entire segment right here. Okay, so 5 plus 5. So AB is 10. Okay. BC is equal to this entire segment. So 10 plus 5, which is 15. CA is equal to is this entire segment. Okay. So 5 plus 10. So this is 15 as well. Now, they want us to show that ABC is isosceles. So remember what an isosceles triangle is. It's a triangle with two equal sides. Okay, so since BC is equal to 15 and CA is equal to 15, ABC is the isosceles. Okay, so since BC is equal to CA, they both equal to 15, triangle ABC is isosceles. Okay, so let's go to this example. So in numbers 2 and 3, line PQ is tangent to circle O at P. So P is a point of tangency. Line SQ is tangent to circle O at S. So S is another point of tangency. And line OQ intersects circle O at T and R. Okay. So let's think about this for a second. So since QS and PQ are both tangent segments drawn from the same point, QS is congruent to QP. Okay. Now, since the tangent line and the radius intersect at the same point, this is a right angle and this is a right angle. Okay. Now, radii of all the same circles are congruent. In the same circle are congruent. So this PO is congruent to OS. Okay. All right, so now let's look at what we have here. So if OP is 15, so OP is 15, and PQ is 20, we want to find OQ and QS. Okay, so we can actually find QS pretty easily because we just said QP and QS are congruent. So if QP is 20, then QS also has to be 20. Okay. OQ is a little more challenging for us to find. So this is OQ. Now, remember, this line that's drawn from that external point to the center is our hypotenuse. Okay, and since we have some right triangles in here, right angles, these are right triangles. Okay, so we can use Pythagorean theorem to find OQ. Now, this is going to be our A, this is going to be our C, and remember, hypotenuse is always our C. So we could do 20 squared plus 15 squared is equal to C squared. Okay, so we can solve this for C. So 20 squared is just 400. This is 625. Now the square root 625 is 25. So the length of OQ is equal to 25. Alrighty, let's go to the next question. All right, so same thing. We have tangent lines drawn. We have tangent segments. Tangent segments drawn from the same external point are congruent. So QS is congruent to QP. Okay. Radii are congruent. Okay. Our tangent line is our tangent segment and our radii intersect at the point of tangency. So this is a right angle and this is a right angle. Okay. All right, so let's look at what they give us. So OP is 10. And PQ, oh, sorry, this is OP. And PQ is 10. All right, so we first want to find QS. Now, QS is the same as QP. So this is 10. Right? Radii are the same. Now we want to find the length of OQ. So OQ is this line. Remember this external line. Or not external line, but line drawn from the external point to the center. Now, this is our hypotenuse. Okay, so we're going to do 10 squared plus 10 squared is equal to C squared. Okay, so 10 squared is 100 plus 100 C squared, so 200 square root of 200. So we have 10 times the square root of 2, which is OQ. Okay, I just simplified it in radical form. All right. So that was lesson 4, I believe. Yep, lesson 4.